I'm going to talk about kind of more of a real-world application to using oaScript and oaxPop. In the past, we've talked a lot about oaScript and oaxPop in theory, introduce what they are, but we don't really go into how it can benefit you and what some companies are doing with this in real life. And so, I'm from Intel. I gave this presentation about a year and a half or so ago at the SI2Con, but I wanted to also give it here as well to kind of reiterate what we've done and also give an update on what we have done in that time span since then and what we have planned for the future. So as far as what we're going to cover, I'm going to spend just a little bit of time going over oaScript and oaxPop. They've been covered to some extent already, so I don't want to repeat things over and over again for you, but I do want to give a little bit of an introduction so that you know a little bit more about what they are. But the bulk of the presentation will be talking about Intel's experience with using oaScript and oaxPop, and we'll go through some of the things that we've done in creating a framework for developers. We have some feedback on performance that you can expect in using these packages, and then go through a couple of applications that we've created using oaScript and oaxPop, specifically a density calculator and a methodology checker that we have, and then go through some of the, again, the future plans that we have for this. So just real quickly at a high level, oaScript, again, it's been covered here a little bit, but it basically is a standalone direct interface to OpenAccess. You can use one of the 4 supported languages, Perl, Python, Ruby, or Tcl. And by using a scripting language instead of the C++ interface, you're able to very quickly create your own OA application by just using that scripting language. You don't have to have any special knowledge in C++. You don't have to compile. You can very quickly get up and going. As far as performance and memory in oaScript, it's very comparable to a C++ application. The only extra overhead would be interfacing with the scripting language, and most of the time that's not a problem. There are cases where it is a problem, and I actually talked to that a little bit later on. And one of the really good things about oaScript is that it matches the OpenAccess API pretty close, I mean identically essentially. And so there's a very well-documented HTML document on the OpenAccess API for C++, and that can be used also for the oaScript. And in fact, again, one of the updates on that we actually have a translator now that will convert that documentation into kind of the idioms or the native syntax of each of the supported languages, so it feels even closer to that language. So, you don't have to do that kind of translation in your head when you look at it. As far as convenience functions, we have added some convenience functions to do some of the heavy lifting, especially things like converting the scalar names through various namespaces and things like that. So there's some kind of, we definitely cover the full C++ API, but then we add a little bit of convenience that you would, most people writing in scripting languages would come to expect. We initiated the oaScript working group in 2009, and unfortunately this slide has not been updated since I last gave this, and so that makes it 8 years now, not 6. It's very stable. It's used in production at Intel, and I'm aware of it being used elsewhere in production as well. So it is very stable as far as what you can rely on. This is just a graphic showing how it works. Again, I'm not going to spend too much time on this because we already talked about it, but essentially the key thing here is that all of these scripting languages connect to the OpenAccess API, and this is the same API that any vendor would use if they wrote their EDA tools. So you have access to the same functions that they do. You have a consistent set of interfaces, so we have a common framework using Swig, which was mentioned earlier. And then we have some type mapping that converts to and from the language, basically. So that's, again, it's common. Adding a new language is a little bit of a chore. It takes time, as was mentioned earlier, alluded to earlier with the Go language. But overall, as far as what is being done and the complexity of it, it's pretty efficient and very, again, very consistent. So that was oaScript. So for oaxPop, this is basically a high-speed polygon operations library that we have. So if you look at the OpenAccess API, it has some classes available to describe layer relationships or kind of operations that can be done. And what I mean is like an AND operation, an OR operation, XOR, that kind of thing. But it didn't have any kind of a built-in engine to actually perform that operation on a set of shapes and provide a result. So there was a gap. And it just so happens that in 2008, Intel, another group at Intel, had created a high-speed polygon manipulation library that they had used for our own internal EDA features that we needed. And they thought, hey, let's go ahead and contribute this as open source, not necessarily just to the EDA industry, but to the community at large. And they did that in 2008. And it became a part of the Boost library, and it's called Boost Polygon. And it sat there waiting to be discovered until I thought, hey, there's this gap in OA, and there's this library sitting here, and we got OA sitting over here. Let's try to bring these things together. And that's what we did. So we basically started a working group, and the working group was started in 2012, and we had done some work before that. And that allows us to basically take an OA primitive object, and without having to do anything with it, you can say, I want to put this object into this polygon set, and then perform operations on it. So it's very convenient. It's also wrapped in oaScript. So the way that we set up oaScript is it allows extensions to be very quickly also wrapped in those target languages. So we have it available in these scripting languages. And this shows it kind of working together. So basically, at the core, we have the OpenAccess API. Again, all applications obviously connect to this using this API. And then we have the extensions where we have oaScript going to the languages that I showed previously. And then oaxPop is basically the intermediary between OA and Boost Polygon, which does the heavy lifting as far as the operations are concerned. So oaxPop exposes the features that Boost Polygon had, which were the primitive functions I mentioned earlier, and or XOR and NOT. It also adds in the unified layer model, thanks to Jake. I think Jake, those are basically a set of predefined, very specific descriptions of shape relations that were bundled into a single word. And so with that, we can use a higher level word to basically select objects that meet a certain criteria, like one certain set of shapes that are fully contained within another, and so forth. And this is just, this is really just a small subset, but there are about a few dozen, I believe, that are there. There are also area selection operators, so any kind of polygon that meets a criteria of, greater than, less than, or equal to a certain area of that shape. So that's there. And then there are, of course, resize operators to allow shapes to expand or contract. As far as performance is concerned, this is always a big question on people's minds, especially when we deal with very large databases. When the Boost Polygon contribution was made, that was already thought about before that point in time. And since then, further performance improvements have been made. And there are different buckets within oaxPop. So you can have an any angle polygon, which allows, as the name implies, any angle whatsoever. Or there's also another bucket that's a 45-degree angle only type bucket, or a 90-degree angle bucket. And each of those offers better performance. As you go towards 90, you have the best performance. If you go down to any, it's still very good performance, but it's not as great as 45 or 90. And so within EDA, I think most of us probably can at least go to 45 degrees, and in some of the more advanced nodes, you don't even need that. You can just stay with 90 and get really good performance. But what I did was I wanted to prove that that it had really good performance. And so I took some commercial applications that worked with shapes, and I changed the names to data 1, 2, and 3. And I scrambled the values to avoid anybody trying to match them up to any particular application. But the data in this table does represent sources from various commercial solutions in this space. And this is a very simplified example. It's not representative of full EDA, obviously. These are all flat shapes. I synthesized 50 million shapes on layer A, 50 million on B, and I believe it was just that. I can't recall, it may have been randomized to some extent, but it was just intersections like that. The GDS size was 6 gigabytes, and I only used a single thread on all cases. And what I did was I highlighted the best performance out of the set for the primitive operations and or XOR and NOT. And as you can see, oaxPop was the fastest performance in all categories except for the AND, but at least with a few there. But I think the takeaway here is that it is competitive. It's able to do what it needs to do very quickly. I didn't mention there are other open source solutions for polygon manipulations, and they don't even come within the ballpark of this. I mean, you can go online on the Boost Polygon page. It shows graphs and comparisons with CGAL and a few other open libraries, and they don't even come close to touching this. Okay. This is a further analysis of the performance. This is not comparing anymore. This is just showing the runtime within itself. And this shows the four primitive operations here are on the leftmost columns, and then the ULM, those layer operators are described over here. And typically these layer operators are pretty much going to be a combination of these primitives. So they're always going to be a little bit more than the primitive operations. And they're not necessarily optimized in the sense that we didn't rewrite the code flat to basically work the most optimally. But it could, of course, be improved over time to do that. But the easiest thing to do was to basically take the existing operations and work with them. And there could be further improvements on this. I think one of the biggest gaps that exists today in Boost Polygon and oaxPop is that when it sounds very basic, but with the touching operator, when you say, does this shape touch another shape, the question is does it include the corner touch? And so that's a basic thing, but more significantly, it impacts many of the other downstream ones. And in fact, probably this budding or coincident is, as you can see, is very impacted by something, and that's likely one of those things. And so we have looked at trying to improve the code base to include that as an extension, an option to the function call. But as we all know, we have day jobs that prevent us from doing that kind of thing all right away. So, but it's there for the taking when the time is right. Okay, so let me switch real quickly now to Intel's experience with oaScript and oaxPop. I was one of the original members of the oaScript extension, along with a few others in the room here. And because of that, we kind of got going pretty quickly. We started using oaScript in some small production areas around 2011. Of course, we were using it in test from the beginning as well. But then we really kind of stepped it up and went into actual deployment in some of the packages that we distribute to our end users. And we did that in 2014, and that's what I'll talk about here a little bit. And Intel being such a big company, you can imagine you have all these smaller companies within, in a sense. Everybody has their own way of doing things. And so we actually are using each of the languages in oaScript, depending on the business group or the familiarity that the person has. But it seems like Python is picking up some steam, as well as Ruby probably as well. As far as areas of opportunity, so most of the time we do what we need to do within the EDA tools themselves, but there are times where there may be Intel-specific features that need to happen, and we may need it to be deployed across multiple editors. And so to be able to create and deploy something that's centrally defined saves us time and effort in support and in documentation, training, and that kind of thing, as far as consistency is concerned as well. Some of the other applications, in fact, this is another one that's ramping up right now big time, is automated QA flows, basically, to read and write OA data. And one of the things I'm working on now, it's not necessarily part of this presentation, but is an automated test case generator, which basically can synthesize test cases very quickly in an automated way. And then it actually stores within the OA database the results of the test after the test, the check is done. And then it reads from the OA and reports out. So OA becomes almost like it doubles as a design database and a storage location for the results of the tests that can be pulled from and reported on. So that's a big emerging thing that's going on right now. And then as far as OA data mining, you may want to query your design to get information about how much hierarchy is there, what layers are used, that kind of thing. It works very well for that. Okay, so as far as bringing it all together, so to make this convenient for developers and to make it more of a deployable package, we created what we call a framework generically, and it basically includes OpenAccess, oaScript, oaxPop, Python, Qt, and any other libraries that we have that need to be deployed. And these are created within a package, much like an EDA tool, if you will. And there's a wrapper that basically will set all the variables that are needed and basically gets you set up. And if you use this package, you can just right away start using it for deploying your applications, creating and deploying your applications. Because we're using a scripting interface, we don't need to compile, and it's very portable. So. We do have some automation that we use that I'll highlight with us specifically in a few minutes here, but that basically will work with the layout editor as far as inter-process communication is concerned. So you can see you may have a command line interface to this, or you may have one or more layout editors. We use inter-process communication with a very lightweight front end on the layout editor side that basically sends signals to the code, the OA code, and tells it what to do. And so it feels like you're in the editor doing something, even though it really is a separate application. Okay, so we kind of do that, and again, we use a wrapper to kind of set that up. Beyond that, we added our own convenience functions, even beyond what oaScript offers. There are just certain functions that are done frequently, and rather than rewriting them multiple times, you kind of get tired of it after a while, and you say, hey, it would be nice if I just had this available. We include that in our own framework as well. Just simple things to get the LCV, the library cell view, in some formatted text string, getting a layer from a name, and things like that. So we did that, and we added this little X in front of it, so we knew we didn't want to get people dependent on it and not know if they were using the actual OA API or this, and to keep that separate so that people knew when they were using an OA function versus this extension. We added the prefix on there. So we did that. Okay, so this is one of the two applications I'm going to highlight. We have many more, but these are the ones that I felt were worth demonstrating what we've kind of done with this. One of them is a density calculator. It's not a complicated concept, really. It's just a global density. It's not a window or shifting window or anything like that. It's just a global density, which is a calculation of a layer versus the absence of a layer in a given region. Okay, and so what we had before is a solution that, the sign-off solution is the users have to actually go to GDS2 data, run something externally, and bring it back in. And it doesn't have this level of interface. And so they said, hey, we need something where we can get an answer quickly. We needed to deploy this for multiple editors. And so we created this application, okay? And basically, it supports all of the layers, and it supports full hierarchy. As far as performance, we we had a test case block that we used. It only had 4 layers of levels of hierarchy, but it's been used on much bigger than this as well. But for our performance testing, that was what we used. It had 19 layers and about 277,000 shapes. The runtime on that for all layers was 1 second, basically. We used a C++ helper class for that. I'll talk about that on the next slide here to kind of give you an idea of some of the performance gotchas. But we also have a query here like get bbox. When you click on that, it sends a signal to the editor saying, I want you to give me a bounding box. It prompts the user for a bounding box. They draw the bounding box in the editor. It sends the result back and puts it into the text field. So that's one example of inter-process communication. The user doesn't really know necessarily that they're outside of the editor. Okay.
James, outside of the code that you would write to generate the graphic there, how many lines of oaScript do you actually use to do that?
For this one, for the IPC or the specifically, or the whole application? This application was actually very simple. I would peg it at definitely less than 1,000 lines of code. Probably 500 to 700 would probably be more accurate. Most of the
Did that include the graphic? Or?
Yeah, that included the graphics because we used Qt, so we were able to draw the GUI, which generates code, of course. So
if you were to take away the Qt code, how many lines would you actually have?
It's probably 200 or less easily. I mean, even that's too. I mean, the most of the code is the interface. Right. The actual operation comes down to like 2 lines of code, really. And in fact, on the next slide, I have actually a few snippets that show how simple it is with oaxPop. But yes, it does narrow it down. The actual operation is simple. You just say, give me a fig set. This is my area, which is a rectangle. You get an area from that rectangle, and these are the shapes that are in that rectangle. Now just divide the areas by each other, and that's the result. Do the arithmetic. That's it. So it's really, not that complicated. We also, unfortunately, I hate to say it, but we must have been under the gun. But we did do some derived layer hard coding in the code, which did some other operations to kind of prepare. I didn't show it here, but because it may have more process details from us in there. But it basically prepared data a certain way for a more accurate density calculation. So, yep, yeah.
What kind of Qt version did you use? Did you use the Qt bindings?
The Qt, we use the Qt bindings. Yeah, we have Qt bindings. I don't recall. I have a colleague of mine who is more of an expert on the Qt side of things, but
bindings, I think limited to 5.8 or something.
Right. Yeah. So, but we did wrap. We used the whole Python binding, PySide or something like that. It's a PyQt. Yeah, that's right. This is all written in Python, by the way. Yeah, that's a key thing. This whole thing's written in Python. It uses Python Qt interface, and uses oaScript and oaxPop. Exactly. Yeah. Okay.
Can we interface Qt with oaScript directly without we have to pass through a script language?
As far as what Qt supports, you mean?
Yeah, if you can do it, for example, if we do the interface with Qt, can we interface directly with the C++ object for script, or we have to pass through a scripting language like Python?
Right. So I'm not sure I fully understand your question, but Qt is available in C++, but there are some ports to other scripting languages like Python, for example, and the same thing for oaScript and oaxPop. So the reason why we chose to go with Python again is that we were able to very quickly create an application without having to compile or anything like that. So, okay, let me just move on here. So as far as performance is concerned, when we first did that previous application, the density calculator, the runtime was all right. It wasn't too bad, but it was slow, and we realized, hey, there's some opportunity for performance improvements. And we did some profiling, and it came down to this specifically. So actually, since this presentation was put together, and since this experience, we actually have put in the ability in oaxPop to directly take a shape occurrence and put that directly into an object, a fig set object. And so all of this code here including determining if it's an actual shape that is representable inside of a fig set within oaxPop. All of that is now has been addressed and is now part of the built-in system, which is really, really, really super easy, because if you ever do this, it literally becomes one line of code where you basically initialize your fig set up here, and then that one line is just adding the ox shape to the fig set, okay? But still, there is, even with that feature, there still is a performance hit to transferring control from the query to the language every time it encounters a shape, which can be hundreds of thousands or millions of times. And so every time you do that, that's where you're going to see a performance hit with oaScript, because it has to convert everything into the scripting language, run the function, and then convert it back to the system, basically. And so so what we did was we addressed that by creating a small C++ class, very similar to Larg's presentation, and we basically wrapped what we needed to. And by doing that, we got about a 400x to 2000x improvement, depending on the test case that we used. I think that this would increase with size. I think that the design size would exponentially take longer using the old system. But we don't have much more data beyond that, other than it was definitely compelling to use this this improvement, of course.
I noticed that you're using the names for the layers and the
Yes.
purposes. Is that now part of oaScript?
That's not, it's a very good question. It is not. That was just a little syntactical sugar that we added to this thing to make it easier to use, yeah. But yeah, I think the problem with putting that in OA is that sometimes you kind of lose control as to what happens if it can't look up the layer successfully. Like what should you do in that case? And that's why, even though it adds more burden to the developer, it allows them to have control of how to respond to that. So, but
These are your X_function you mentioned earlier, right?
yes. So in this case what I'm doing is this is my specialized class. I set the region, and then I just basically do query. And actually, I can do multiple queries on that region. So it's a little bit different than the OA version. And this is, So and it basically, it's collecting objects and putting it into the fig set is what it's doing behind the scenes. Because this is a common thing to do. So
Is this C++ based?
yes.
Is it part of the framework that you were talking about?
Yes. Yes, it's part of the framework. So it's our own code. I'm going to talk at the end. I actually, in fact, I'll just bring it up now. It doesn't matter. But we had a request to contribute this as part of oaxPop, and I actually have legal approval from Intel to do that. I have not taken the time to do it, which I apologize for. But we can, coming out to these things gets my mind going again. I really got to get this out here. So I'll probably be contributing this at some point. All the checks have been done. In fact, we even voted on it, I think, as part of the working group. So the working group agrees, yes, we want to bring it in. I've got approval. It's just a matter of actually doing it. But yeah, I do intend to contribute this, so. Okay, so the other application is a methodology checker. So we have certain rules that we want our designs to follow. These are not necessarily manufacturing type of rules or design rules. These are kind of compliance checks, making sure the boundary has the lower left corner at the origin of the coordinate system and things like that. And so again, as you can imagine, consistency is very important. And so by developing this one time in this application standalone, we can have multiple editors connect to it and perform the exact same checks and maintain that set of checks in one package, basically. So again, it's hierarchical, and this is certainly not a list of all the checks. Again, I kind of filter it out to things that are innocuous enough or generic enough to where it doesn't reveal too much about what we're up to. But here are some of those one-liners. So if you want to find out if let's say, for example, a wire is on grid, and you create a fig set that contains either an imported or a synthesized grid. You can either synthesize your grid doing a for each loop or read it in through some format and populate a fig set that way. And then you take your actual wire shapes, put them in another fig set, and it really comes down to one command. The error results is any wire that is not fully within a grid. That's it. And you can take that error set and you can convert it into markers that become navigatable, okay? Another one, standard cell row grid, same thing. You can build up odd or even rows that are interleaved, and you basically can take the boundary, a queried boundary of the each standard cell instance, any boundary that kind of creeps out of the row is an error. It's not placed on the row properly. As far as floating labels, so one thing we did with that was we created a little rectangle, since you can't, actually oaxPop doesn't support single points, which is probably something that should be improved at some point. But basically, we synthesized very small rectangles exactly at every origin, and then you can find what labels are floating. They don't have a material underneath of them. So you say labels without, and deduct the any labels that are actually touching a shape. And again, we're using a higher level name here, so touching, and so we can say any labels that are essentially not touching a shape, they're floating. So very simple as far as what you need to do. Okay, so as far as limitations, there are some limitations. You do have to save the design because in most cases the editors aren't open enough to allow you to work on the runtime memory. And so what we've done is we've added another IPC call that when the user hits run, it sends a signal to the application saying save the design. It saves the design. It says, okay, go for it, and then it reads it in. So that was mitigated that way, but it is kind of a workaround. Also, I think going off of what Ted was saying, so working with P cells or anything that requires a plugin is just very difficult to manage. It is possible, but we had to deal with a lot of things through trial and error, and we eventually overcame it. But it still is something that you kind of have to work with, basically. There are no native DRC checks within oaxPop, so a lot of times we want to perform some kind of a check on shapes. That's not in there by default. Of course, you can build your own relatively easily, but it would be nice if that was part of it. There are no edge, vertex, or point operations that are really exposed, so that's kind of a limitation as well, as far as oaxPop's concerned. Okay, as far as the roadmap, so I mentioned a few minutes ago, we do need to still contribute those shape query improvements. Everything's ready to go, we just need to actually do it, and that involves a little bit of cleanup of the code. And then as far as multi-threading, we know that this is something that we probably can do in the future, but we don't have any pressing need from the user community right now or anybody willing to step up to do it. And so again, it's a matter of time and just doing that. And then I mentioned just a minute ago about the vertex and edge-based operations. So basically, to summarize, the oaScript and oaxPop extensions are very stable. They're available through SI2, and we are very, very heavily dependent on them now. It represents one of our core capabilities, I'll be honest with you. It's very important to us. By using these, both of these, you can create very, very powerful OA-based scripts that basically work directly with the OpenAccess database. And Intel has successfully used both in our production applications. We've been able to do that with standalone applications and also applications integrated in the editor, and the performance is really great. So, yeah. So, like I said, we're very, very happy with it, and it's extremely powerful. I guess that's it.